Welcome to the Explainer. So today we're diving into one of the absolute most notorious members of the bacterial world. We usually just think of it as a generic germ, the kind that completely ruins your weekend with food poisoning. But in reality, it is an active, highly sophisticated cellular burglar. We're going to decode the incredible mechanisms of Salmonella, and I promise you, by the end of this, you're going to understand the massive, literal life or death difference between your common stomach bug and the deadly systemic invader known as typhoid fever. Let's get into it. Okay, let's dive into this roadmap. First up, we'll look at the Salmonella family tree, then the microscopic cell heist, followed by typhoid, the stealth invader. After that, we'll walk through the 5 stages of typhoid, and finally, treatment and prevention.
All right, Section 1, the Salmonella family tree, from animals to us.
Now, you might be wondering, does the name come from the fish? Actually, no. It's named after a veterinarian, Dr. Daniel Salmon, whose lab was the very first to isolate it. And honestly, naming it after a vet makes total sense, right? Because most non-typhoidal Salmonella infections actually originate in animals. We're talking cattle, hogs, and poultry. It lives in their guts, gets pooped out, and, well, eventually finds its way into our food supply. Just to put the sheer scale of this into perspective, there are up to 1.5 million cases of Salmonella food poisoning every single year in the US alone. It is incredibly common. You can get it from undercooked chicken, raw eggs, or even just unwashed lettuce that happened to be in the wrong place at the wrong time on a busy farm.
So what's really fascinating here is how this bacteria actually makes us sick. It's not just releasing some poison into our tissues. Instead, the cell wall of this gram-negative bacteria has this component called lipid A, which acts as an endotoxin. And let me tell you, our bodies absolutely despise lipid A. The second our innate immune system detects it, it triggers this massive, overwhelming inflammatory reaction. So you feel terrible not because the bug is directly destroying your tissues, but because your own immune system is basically going scorched earth to fight it off.
Moving right along, Section 2, the microscopic cell heist, a smash and grab. Let's think of the standard non-typhoidal infection as a desperate smash and grab break-in operation. Just to reach the cells lining our bowel, the enterocytes, this bacteria has to survive a brutal biological obstacle course. It has to endure a bath in highly corrosive stomach acid, then toxic bile, fight off all the competing organisms already living in your gut, and then literally swim through a thick layer of intestinal mucin. The fact that it survives this massive gauntlet really shows just how insanely resilient this organism is.
And this brilliantly illustrates what happens next. When it finally arrives at the cellular surface, the bacteria deploys this incredibly complex mechanism, known as a type 3 secretion system. It's essentially a microscopic syringe used to inject enzymes directly into our host cell. These enzymes actually hijack the cell's structural actin, forcing the cell to swallow the bacteria whole and build a custom protective bubble around it. We call this a Salmonella-containing vacuole, or SCV. It literally builds its very own safe house right inside our cell. Crazy, right? Once inside that safe house, it's exactly like a burglar cutting the alarm wires. The SCV's membrane gets modified so that the cell's natural defense weapons, the lysosomes, can't bind to it and kill the bacteria. So the bacteria just sits there, reproducing safely inside its contrived sanctuary. But our innate immune system isn't completely clueless. It realizes something is wrong and releases interleukin-1 beta, which is a super powerful inflammatory cytokine. And that's what causes that terrible hit-by-a-cement truck feeling, the severe fever, the aches, the dehydration. It's essentially a messy, fiery police response completely localized to your gut. All right, on to Section 3, typhoid, the stealth invader. But what happens when the burglar doesn't just want a quick smash and grab? See, if normal Salmonella is a petty thief, Salmonella typhi is the absolute master thief, and it escalates the situation dramatically. While standard Salmonella infects the large intestine, S. typhi heads straight for the distal ileum of the small intestine and intentionally targets our macrophages. Now, macrophages are the exact immune cells designed to hunt down and kill bacteria. As the source material puts it so perfectly, it's kind of like a bandit breaking into jail. It actively seeks out the guards. No way, right? So, how exactly does it survive those guards? Well, Salmonella typhi is equipped with a or virulent carbohydrate capsule. You can think of this as a molecular stealth suit. It masks the bacteria's outer structures, making it so much harder for our immune cells to get a clear lock on it. And because of this stealth mode, the host usually feels almost no initial response. There are no massive alarm bells, no cement truck feeling right off the bat. It just slips in completely undetected. Once inside the macrophage, the bacteria completely takes over mission control. A specific protein called Pho/G switches on, unearthing hidden survival genes right there in the phagosome. It then pumps out bacterial proteins that totally neutralize the macrophage's deadly lysosomes. So instead of killing the bacteria, the macrophage goes about its normal business, traveling through the bloodstream and lymphatic channels, unwittingly acting as a microscopic getaway car. It's literally spreading the infection systemically. Eventually, the macrophage becomes so stuffed with bacteria that it ruptures, flooding the entire body with those dangerous endotoxins.
Let's move to section 4 and see how this builds. The 5 stages of typhoid.
Once that systemic spread actually gets going, we see a very distinct, prolonged clinical timeline. Unlike standard food poisoning that hits you in a matter of hours, typhoid takes its time. It starts with a 10 to 14-day incubation period where the bacteria is quietly setting up shop in those macrophages. Then you get about a week of active invasion with low-grade fevers as those macrophages travel to the liver, the spleen, and the bone marrow. The storm clouds are just slowly, silently building up.
And then we hit the peak. This is known as the fastigium. The macrophages rupture, endotoxins pour out, and a massive cytokine storm absolutely erupts. Patients experience terrifying 105-degree fevers and profound delirium. Actually, fun fact, the word typhoid comes from the Greek word for smoky or hazy, perfectly describing the patient's severe mental confusion. About 50% of patients also develop these macular row spots on their abdomen, these little red dots that actually contain living, viable bacteria. Following this peak is the lysis period, where the body slowly clears out the endotoxin over a couple of weeks, and finally, a really long, exhausting 3 to 4 week convalescence, or recovery period.
But here is the wild part. The story doesn't always end with recovery. S. typhi is notorious for creating a long-term carrier state. Because it travels to the liver, it easily filters right down into the gallbladder. If a patient happens to have gallstones, the bacteria builds these hardened, crusty biofilms right around the stones, safely locking themselves away from the immune system. From this ultimate hideout, they just constantly shed back into the intestines, continually reinfecting the host and spreading back out into the environment.
All right, our final stop, section 5. Treatment and prevention. Knowing this is a terrifyingly efficient pathogen, how do we actually fight back? Well, the crucial point is that you absolutely must treat these two versions differently. For non-typhoid stomach bugs, antibiotics are largely useless. They just wipe out your good bowel flora, which are actually trying to help you fight the invader, and taking them can actively prolong your illness. Seriously, don't demand antibiotics for standard food poisoning. Typhoid, on the other hand, is a systemic blood infection. For typhoid, intravenous antibiotics, specifically things like third-generation cephalosporins, are highly effective and literally essential for survival. Now, looking at this history, these treatments have been a bit of a double-edged sword. Back in the early 1950s, chloramphenicol was our first real weapon, but it carried this rare, terrifying risk of causing fatal aplastic anemia by shutting down the patient's bone marrow. Today, we rely heavily on modern drugs like ceftriaxone. It's incredible, but it does require an IV. In areas where IVs just aren't an option, oral fluoroquinolones are used. And this is a massive issue for global health, because bacteria are so good at swapping genetic material, antibiotic resistance is growing rapidly. And the stakes for maintaining these effective treatments, they are incredibly high. While it's true that 85% of people might survive an untreated typhoid infection, a 10 to 15% mortality rate is just a devastating toll when you realize there are an estimated 9 to 10 million cases globally every single year. Sadly, this heavy burden falls almost entirely on the developing world, where sanitation and medical access can be really limited. Fortunately, alongside antibiotics, we also have vaccines. Now, the very first typhoid vaccines just injected whole dead cells right into your arm. But remember Lipid A? Injecting dead cells meant you were injecting endotoxins, so the vaccine itself actually made people feel genuinely sick with chills and aches. Plus, the immunity just didn't last very long. But modern science solved this beautifully. Today, we either use a highly purified version of that stealth EV capsule attached to a protein carrier, or we use a live weakened bacteria taken orally. Both of these trigger strong immunity without causing the actual disease. In the developed world, we've largely pushed typhoid out through this thin, almost invisible wall of modern sanitation. Things like water treatment, secure sewage, and vaccines. But as we wrap up this explainer, I want to leave you with one final thought. Typhoid is an opportunistic master thief, always waiting in the wings. When natural disasters, like severe flooding, destroy our fragile sanitation infrastructure, clean water mixes with sewage, and these bacteria can immediately return. So it really begs the question, are we truly prepared if that thin wall of modern sanitation ever breaks down?
Thanks so much for joining me to explore the incredible microscopic world of Salmonella. Stay curious, and I'll catch you in the next explainer.